In this video, we're going to cover the fundamental concepts that we will use throughout this course, which is static behavior of mechanical systems. So what we're going to do is to simplify real mechanical systems. We're going to use some idealizations or simplifications. Okay, so we're going to make these following assumptions very often. So we're going to assume in a lot of cases that we can treat an object as a particle. So a particle is any object where its relative size is not important. So the particle or the object's geometry will not play a role in how a force interacts with a particle. So for example, if you had a volleyball, I apologize, alright, and we had a tennis ball, alright, if we hit them both, if we applied a force to the tennis ball and we applied a force to the racket, to the volleyball, we'd expect both of these systems to follow a parabolic motion. And hopefully you're familiar with that from physics 1. Alright, so both of them will follow a parabolic trajectory, so the size of the ball will not affect the motion of the geometry. So therefore, we can assume that both of these balls, the diameter of the ball is not important. The only thing that's important is the force that's being applied to it. That will affect its motion. All right. So a rigid body is another assumption that we'll often make in this course. Is that, and what a rigid body is saying is that we will consider an object to be a rigid body if it is a collection of particles that will not deform significantly under load. The big benefit of this assumption is that you can ignore what the material properties are made out of. So, for example, if you had a bolt here, okay, and so I'll draw it in 3 dimensions. Alright, and you want to tighten this bolt or loosen this bolt. What you would often do, or what you would typically use, is you would use a wrench. Okay. Alright, and the amount of force that you apply or torque that you apply to this wrench is only dependent on the force that the operator applies to this wrench times the length of the wrench. It doesn't matter what the wrench is made out of, it won't affect the amount of torque that would be applied to the bolt. Alright? And then the final assumption that we'll use in this course, often used in this course, is the assumption of a concentrated force. So oftentimes we will treat forces that are applied over an area as being applied as a single point. We can often do that in the cases of when a pressure is applied over a very small area relative to the overall size of the object. So a simple example of this would be if you had a bicycle, for example. So, alright, so a bicycle alright. So for a bicycle, alright, the bicycle is held, I guess, or is held at or is supported at the ground, or connects with the ground at the 2 wheels. So at those wheels, we can say that the force of the weight of the bike and the weight of the rider on the bike is supported by the force that's applied at the two wheels. But if we look closer at the wheels, what really is going on is that you have a very small area that's under the tire that supports the load. But since this area is very, very small compared to the overall dimensions of the bike, and the size of the bike, we can treat this pressure as a concentrated force. So we can treat the pressure applied by the ground as a concentrated force. All right. So the rest of this course, in addition to these concepts, is really built upon Newton's laws of motion. So if we go to the next page here, I just want to review Newton's three laws. So if you want, I'd recommend actually is that if you just took physics, try to take a second, stop the video, and try to recall these three laws of motion on your own, and see if you can remember all the three laws. And then you can watch the video, or you can check the handout and see how well you were able to remember. Okay, so without any further ado, Newton's first law states that a particle in equilibrium will remain in equilibrium unless an external force acts upon it. Alright, so equilibrium we can define as the sum of all the forces acting on a particle is equal to 0. Alright, so basically, and so if that is the case, the particle will be not accelerating, or basically it means its velocity is constant, so its velocity could be equal to 0, or it could be equal to some constant value. Alright. So what Newton's second law states is when the sum of the forces of a particle are unbalanced, so if the particle is not in equilibrium, so if the sum of all the forces acting on a particle does not equal 0, the particle will accelerate Alright, and then this acceleration is proportional to its mass and the applied force. Alright, so this is a pretty famous equation that the force applied to an object will be proportional to the mass of the object and the acceleration. So F here is the force. Alright, this is a vector, which means it has magnitude and direction. The mass of an object is a scalar value. Right, and then the acceleration is going to be a vector as well, so it'll have a magnitude and a direction. Alright, and then the third law in this, Newton's third law, is when an object applies a force on another particle, an equal and opposite of forces applied back. So for every applied force, there's an equal and opposite force. Alright, and then the last law, Newton's law, important law, is Newton's law of gravitational attraction, which states that the force between two objects, force of gravity between two objects, is proportional to the mass, the product of the mass of those two objects divided by the radius squared between the two objects times g. All right, so g is a constant, is equal to 66.73 times 10 to the minus 12 newtons per meter squared per kilogram. All right, and then r is the distance between particle centers. Or mass 1 and mass 2's centers. Alright. So then, using the Newton's law of gravitational attraction, we can define the weight of an object. So if we go to the next page here, you can say that the weight of an object is going to be equal to the force between an object on Earth times the mass of the Earth divided by times the universal gravitational constant divided by the radius of the Earth squared. Since these three terms are a constant value, we can set them equal to a constant, which we're going to label lowercase g. Alright, and so it will simplify the weight of an object on Earth, we can say is equal to the mass times the acceleration of gravity on Earth. Okay? Alright, and that concludes this video on the basics of Newton's three laws and the primary assumptions we'll make in MME 211.